Here we are trying to discuss formation of a p-type semiconductor, p-type extrinsic semiconductor. The reason for conversion is already mentioned in the last one. The intrinsic semiconductors have low conductivity and their conductivity is highly sensitive to temperature. So for overcoming this, we are adding external elements into group 14 silicon or germanium atoms. The addition of group 15 elements lead to formation of n-type semiconductor. So that is already discussed in another video. Here we are adding group 13 elements like gallium, indium, boron, aluminium, etc. into silicon or germanium, which are group 14 atoms. The group 14 crystal structure demand 4 covalent bond formations with the neighboring silicon or germanium atoms. Group 13 atoms have 3 valence electrons. So all the 3 valence electrons of group 13 forms covalent bond with the neighboring 3 silicon atoms. In the 4th bond, since the gallium group 13 atom has only 3 valence electrons, that is already involved in bond formation with these 3 neighboring silicon atoms. In the 4th bond, there is only 1 electron due to silicon. There is absence of 1 electron because of gallium don't have 4 electrons. So that absence of an electron can act as a hole. Now, since the structure of silicon demands 4 bond formation for stability, these gallium atoms, group 13 atoms, accept 1 electron from the valence band of silicon. So all the 4 bonds are completed for the group 13 atom and it's stable in the structure, but the hole will be formed in the silicon structure. So addition of each gallium atom lead to absorption of 1 electron from the neighboring silicon atoms. So that lead to a hole formation in silicon atom. This hole formation is not associated with formation of a free electron. Generally, the thermal excitation happening in silicon or germanium lead to formation of free electrons and holes in pairs. But here, the electron coming from the valence band of silicon is moving into the valence band of gallium atom. So there is no free electron. The electron is directly transferring from one valence band to another valence band, silicon to gallium, the group 14 element valence band into group 13 element valence band. So that won't create a free electron, but it leads to formation of a hole. So holes are formed due to addition of each group 13 atom. Then free electrons and holes are again formed due to thermal excitation of electrons from valence band to conduction band of silicon. That create equal number of free electrons and holes. The group 13 only create holes. So holes are formed 2 different ways: by normal thermal excitation in silicon or germanium structure and the absorption of electrons by the group 13 atom. So the holes will be the majority carriers compared to the free electrons. Free electrons will be minority in p-type semiconductor. That means NH will be greater than Ne. Still the rule NH into Ne equal to Ni square is valid for all semiconductors. Ne and NH are the hole concentration and free electron concentration after doping. Ni is the free electron or hole concentration, both are equal, known as Ni before doping. These two values are after doping for the p-type or n-type. This value is same, NH and N is same for intrinsic semiconductor before doping. That's written Ni. Now, like N-type is electrically neutral, the P-type semiconductor also electrically neutral. Here also there is a misconception normally. Since holes are more than free electrons, the material has to be electrically positive. But the group 14 atoms are already neutral. Before doping, due to thermal excitation, free electrons and holes are formed in pairs. So the positive and negative charges are equal and opposite, get balanced. Even the group 13 atoms create a hole in silicon structure, that is by absorbing one electron. So the gallium atom or group 13 atom will become a negative ion at the same time when they create a hole. So for each hole created in silicon, the absorption of one electron by the group 13 atom make it a negative ion. So here also the negative ions and the holes created by group 13 atoms get balanced. The total positive charge is equal to the total negative charge. Hence, P-type semiconductor is electrically neutral. If the structure is not clear, these are the free electrons and holes formed before thermal excitation. They are equal in number. The filled ones are the free electrons, the empty round represent the hole. This happens here and there in the crystal structure. This is before doping. Now we can see two negative charges equal to two positive charges which are holes, so totally neutral. When you're doping with group 13 atoms, group 13 atoms absorb one electron. So absorbing or accepting one electron make it negative. The electrons are lost by the silicon atoms, so that create a hole in the silicon atom. So for each hole created in the silicon atom, the group 13 atom becomes a negative ion. So here also equal number of positive and negative charges. So the system is totally neutral wherever the holes are created by group 13 atoms that lead to formation of a negative ion. So the total system is electrically neutral. It is called P-type semiconductor because the majority charge carriers are holes. 1, 2, 3, 4. There are 6 holes and 2 free electrons. Since holes are the main charge carriers, the material is called P-type, where charge is positive, not because the material is electrically positive. Same way, N-type semiconductor is known as N-type because the charge of the majority charge carriers, free electrons, are negative, not because the material is electrically negative. Both N-type and P-type are electrically negative. Thank you.